Hello, good evening, everyone. So, today we are going to discuss the questions based on the week 8th of the course Introduction to Robotics. So, we'll discuss some of the questions based on the lectures which has been uploaded on the NPTEL tutorial on week 8th. So, this is just the tutorial session. And also, this video will be uploaded on YouTube. So, if any students face difficulty later on, can ask the questions on the YouTube as well in the comment section. Or if you're watching the live series, then you can ask the question in the live series also. So let's start with the first question. So in this it is given an incremental encoder generally has three sets of output pulse A, B and Z index. Pick out the right statements made about these pulses. So for this the statement C you can see is true because A and B pulses usually have the same amplitude and frequency but differ in phase to provide quadrature encoding. Okay, so A and B pulses have generally same amplitude and frequency but differ in phase to provide quadrature encoding. So the option C is the correct one. In option A, it has given all the pulses are of same frequency. Yeah, this is just a true statement, but C is the most appropriate. B says that A and B differ in both amplitude and phase. This is also wrong. D also says that the phase difference between A and B depends on operating speed. This is also wrong. So now we'll move on to the next question. That is the question number 2. So the question is, in an AC tachogenerator is used in a particular actuator system. Let E1 and F1 denote the amplitude and frequency of the generated EMF of the tachogenerator at a certain speed. Let the system now operated at half the initial speed while load is unchanged. So the speed of the system is half, but the load is unchanged, and the measured amplitude and frequency of the new generated EMF be E2 and F2. Then in this question it is asking which is the correct option. So in the in an AC tachogenerator, the generated electromagnetic electromotive force EMF is typically directly proportional to the rotational speed of the system it is connected to. So E1 is directly proportional to speed. So speed reduced to half. So here speed is half. So our E2 will be half of E1, okay? And also F2 will be half of F1. So the option C is the correct option for this question. So now we will move to the third question. That is a DC tacho generator is used to estimate the speed of a PMDC motor. The scaling factor between the speed and back EMF constant K of the PMDC motor is 1.9 volt per radian per second, and its armature resistance is 0.5 ohm. During a certain operating condition, the average voltage supplied to the this permanent magnet DC motor at a steady state is 48 volt, and the load acting on the shaft of the PMDC motor is 1.2 Newton meter. If the taco generator generates 9.8 volt at this condition, determine its gain in voltage per radian per second. The answers should be in two decimal points. So we'll solve this question. First, we'll write what and all is given. So in this question, the VA, that is armature voltage, is given, that is 48 volt. Second one is K, that is back EMF constant, that is also given as 1.9 volt per radian per second. Load torque, that is given as 1.2 Newton meter. After that, therefore IA, that is armature current, IA is equal to TL by K. So we will put here 1.2 by 1.9 ampere. So when you do this, you will get 0.6316 ampere. Now back EMF E is equal to V minus IARA. So this is equal to V is given 48 minus IA is 0.6316 and RA is given as 0.5. Here in this question it is given armature resistance RA is given as 0.5 ohm. So here we can multiply with 0.5. So finally we will get, when you calculate this, we will get 47.68 volt. Now the operating speed of permanent magnet DC motor is calculated as E by K. So our E is here 47.68 and K is given as 1.9. So we will get the speed in radian per second, that is 25.09 radian per second. Okay. And now in this question, it is asking to determine its gain. So gain of DC tacho generator is equal to 9.8 divided by this is volt. Eh, It should be in volt per radian per second. And the speed is 25.09. The unit will be volt per radian per second. So the answer when you will calculate it, you will get is 0.39 volt per radian per second. So the answer will be volt 0.39 volt per radian per second. So we'll see the next question now. Like the load of the PMDC motor in question 3 is now reduced to 0. 8 Newton meter. So TL is equal to 0.8 Newton meter. And also, while the supply voltage remain unchanged, what will be the new reading of the DC deco generator in voltage? So now our IA is equal to TL by K. So TL is given as 0.8 now, and K was given as 1.9 volt per radian per second. So you substitute this value. After this, when we calculate this, we'll get IA as armature current as 0.4210 ampere. So back EMF E is equal to V minus IA RA. So this will be 48 minus 0.4210, and RA is given as 0.5 ohm. So after calculating, we'll get this as 47.68 volt. So operating speed is equal to E by K. So our E is back EMF is 47.68 voltage, and K is 1.9. It is given in this question. So this will get as, sorry, here after calculation we will get as 47.7894. So this will get us 25.15 radian per second. So new reading of DC turbo generator will be 9.8 into 25.15 divided by the last time we got is 25.09. So this will be equal to 9.82 volt. Actually, the gain of DC taco generator is 0.39 volt uh, per radian per second. So actually, this is also is equal to gain into operating speed. So we can do this as last time gain we got a 0.39. So simply we can multiply like this also. So the final answer will be 9.82 volt. Okay. So now we'll solve the question, next question, that is the question number 5. So in this question it is given an incremental encoder having 10,000 ppr is coupled to a DC motor used in a certain robotic application. If the shaft of the motor rotates at 1800 rotation per minute, determine the frequency of the index pulse of the encoder in hertz. So one index pulse is generated in one revolution. One index pulse is generated in one revolution, and the shaft rotate at 1800 rotation per minute. Okay, this means that is also equal to 1800 by 60 rotation per second. So this is equal to 30 rotation per second. So 30 rotation means 30 revolution. So 30 revolution in 1 second. Therefore, 30 index pulses are generated. The frequency of index pulse will become 30 hertz. Because in 1 second, 30 index pulses are generated. So the frequency will become 30 hertz. Let me check whether this video is recording or not. Yeah, it's recording. So now we will solve the next question. That is, a sinusoidal PWM scheme is employed for a 4-pole PMSM motor with a carrier frequency of 5 kHz. If the motor is desired to be operated at a speed of 1200 rotation per minute, what would be the frequency of the reference signal used for generating the PWM pulse in hertz? So the frequency of the reference signal should be same as that of the excitation phase voltage. The frequency is given by F is equal to P into N by 120. So N is the rotation per minute. P is the pole, so it is pole is 4 here. So 4 into N is 1200 divided by 120. So we will get 40 hertz. Okay. So we'll move on to the next question. This is very simple question. Just you put all this value in the formula and get the answer. So an absolute encoder has an output of 10 bits. Determine the smallest angular change that can be accurately measured by the encoder in degrees. So it have a 10-bit output. Like encoder has an output of 10 bits. So what is the smallest angle it can measure? So the smallest angle that can be measured by n-bit absolute encoder is 360 degree by 2n. So total angle to be measured is 360 degree. And number of steps is 2 to the power of n. So smallest angle measured is equal to 360 degree by 2 to the power of n. So it will become 360 by 10 n is here 10. In this question, n is 10 bits. It will become 2 to the power of 10. So this will become 360 by 1024. So that is equal to 0.3516 degree. So it can measure, the smallest angle it can measure is 0.3516 degree. So the next question is also depending on the previous question. So in this question it is given the absolute encoder in the question 7 is used to measure the speed of a motor drive system. The pulses from the encoder are sampled using a microcontroller at a sampling rate of 10 kHz. And the speed is estimated by measuring the angle swept in a time span of 10 sampling periods. Determine the lowest speed that can be measured in this case. So here, sampling period is equal to 1 by frequency, that is equal to 1 by 10 to the power of 4. So that is equal to 10 to the power of minus 4 seconds. So time for speed measurement is equal to 10 into 10 to the power of minus 4 because 10 samplings are there. So it will be 10 into sampling period. So it will become 10 to the power of minus 3 seconds. At an event of measurement of the lowest possible speed, there occurs 1 bit pulse change in 10 to the power minus 3 seconds. This means that at the speed of 0.351 degree 16 degrees 15, So 0.3516 degree is swept in 10 to the power of minus 3 second. And time taken for one revolution, that is 360 degree, is equal to 360 by 0.3516 into 10 to the power of minus 3 second. So we'll get this as 1.0239 second. So speed will be 1 by 10 to the minus 3 into 2 to the power of 10. So this is equal to 0.9767 revolution in 1 second. Sorry, here 10 to the power minus 4. The sampling period is 10 to the power minus 4. So speed in rotation per minute is equal to 0.9767 into 60. So that is equal to 58.6 rotation per minute. So the correct answer for this question is 58.6 rotation per minute. So now moving on to the ninth question. A four-pole PMSM is driven using a three-phase voltage source inverter which has a constant DC bus of 600 volt. The inverter is controlled using a sinusoidal PWM technique. The voltage at the midpoint of each leg of the inverter appear as unipolar pulses of amplitude 600 volt, and with the average values varying in a sinusoidal fashion as expected. If phase windings of the motor have resistance of 0.8 ohm and inductance of 1.2 millihenry, and the desired operating speed of the motor is 1200 rotation per minute, determine the DC offset in the phase current following through the windings. So the DC offset is in the phase currents for PMSM and with SPWM operated three-phase inverter is 0. So answer will be 0. So just write this note. The DC offset in the phase current for PMSM with SPWM operated three-phase inverter is 0. So if a stepper motor has 8 poles on the stator and 6 poles on the rotor, determine the number of steps it would take to complete the one revolution. So angle traversed in one step of movement is equal to 360 degree divided by m into nr. Here m is equal to number of stator phases and nr is equal to number of rotor poles. So m is equal to 4 because number of stator phases will be 4 because it have 8 poles, and nr is equal to 6. Therefore, step angle is equal to 360 by 4 into 6, that is 24. So, so this will get as a 15 degree. So number of steps in one revolution is equal to 360 by 15 degree. So this is equal to 24 steps in one revolution. So the number of steps it would take to complete one revolution is 24 steps. In 24 steps, it will complete one full revolution. So now we will see the question number 11. So robotic application demands precise sensing of the angular position of motor shaft to an accuracy of 0.25 degree. It is decided to use an absolute encoder for this purpose. What should be the minimum number of bits that need to be there in the encoder specification for achieving an accurate measurement of the angle? So, in the application of this robotics, it requires the precise sensing of the angular position of a motor shaft to accuracy of 0.25 degree. So, it is decided to use an absolute encoder for this purpose. So, let's suppose n that is equal to 10 bits of encoder have 10 bits. Now, the resolution is equal to 360 by 2 to the power of 10. So this will be 0.3516 degree. Now let n is equal to 11. So with this resolution, we cannot measure 20, 0.25 degree. Okay, because it will overshoot the value of 0.25 degree. Now let's suppose n is equal to 11. So resolution is equal to 360 by 2 to the power of 11. So it will become 360 by 2048. So this will become 0.1758 degree. So with this resolution, we can measure 0.25 degree. So the number of bits will be 11. So minimum number of bits required to measure a smallest angle of 0.25 degree is 11. Okay, because you have to substitute the value of n in this question and check. It should be less than the uh, accuracy required. If it is required 0.25 degree, then it should be less than that. So now we'll move on to the next question. Consider the following variants of motors: induction motor, PMSM, BLDC, on-field DC of the same ratings used for certain application. The motor having the lowest torque density is likely to be. So torque density generally refers to the amount of a torque a motor can produce relative to its size or weight. A motor with low torque density produces less torque for its size, making it less efficient in terms of space and weight. So for this question, the correct option is the unfilled DC motor. So these are just theoretical questions. Coming to the last question, a robotic application use an absolute encoder with the following specification, that is 256 division per revolution. Output give as a simple binary number. The sector in the encoder follows simple sequential binary format. The signal status of the output lines from the encoder at a particular position of the rotor shaft is observed as. So this is 001011 00101100. Determine the absolute angle of the rotor shaft with respect to the reference position. So there is 256 division per revolution. So in one division, angle covered is equal to 360 by 256. So that is equal to, let's calculate, 1.406 degree. So now this is the output. So this output is into 2 to the power of 0 into 2 to the power of 1 into 2 to the power of 2 into 2 to the power of 3 into 2 to the power of 5. So this will become 32 plus 8 plus 4. So this is 44. So absolute angle of the rotor shaft with respect to reference position will be 44 into 1.406 degree. So this will become 61.864 degree. So the correct option is option 6. That is 61.875 degree. Okay. So today we'll stop here only. If you have any doubt, then you can ask in the YouTube comment section also, because this video will be uploaded in YouTube and the link will be provided in the NPTEL portal. So we'll stop here only today. Thank you everyone for joining the today's lecture. If you have any doubt, then you can ask. Or say we can close this session. So we'll close this session. Thank you.